All right, so we'll get started. Homework 6 due on Thursday. Okay. So that's if we can finish chapter 7 by tomorrow. Okay. If not, then the due date will be pushed for a couple of days, I think. And then also, if we couldn't finish chapter 7 by tomorrow, then our exam will be Wednesday, March 10th. Okay, so we'll see about that tomorrow. See if we can finish this chapter. For the in-seat classroom disinfection, I have it assigned to Morgan and Marcus for today. Okay, and so if we are going to have exam 2 Tuesday next week, then we will switch the model of the lecturing. Like we'll have Monday lecture to be online, and then Tuesday we'll meet in class. Okay, for the exam. All right. So today we'll be looking at chapter 7 on electric potential. So this is again it's an analog to the gravitational potential. Okay, so in gravitational potential here, if the object has a displacement in the vertical direction by delta L, then its potential change by minus mg delta L. Okay, similarly over here, for electric field, the electric potential. So if less work done by electric field of the F times delta L, so then electric potential will be reduced by the amount. Okay. So in this case, the analog here is this. If you have a negative charge over here, then positive charge will be moving towards the negative charge. Just like for the gravitational field, if you have Earth over here, object will be pulled by gravitational field in that case. Okay. So electric field for the electric force, it's also a conservative force. So then change in potential energy, okay, is equal to negative of the work done by the conservative force. So this is either delta U equal to minus delta W for conservative force, or in differential form, derivative of U equal to minus derivative of work. Okay. All right. So if you have a conservative force, so du equals to minus F dot dl, okay, so that gives you the work done. And in this case, if we are looking for electric field, then the electric force is what we are concerned. So Q times E gives you the electric field, electric force F there. All right. So then this is du. So if you do the energy divided by Q, then you will have your potential, right? So then potential difference should be equal to potential energy difference divided by Q, okay, or minus E dot dl. So that's in vector form. The dot product of two vectors will give you a scalar quantity, okay? So therefore, if you want to calculate the change in potential energy, then you integrate this equation, okay, here and then there, okay? So integration of dV gives you change in potential difference. Then that equals to minus of integration from point A to B, E dot dl, okay? So that's the equation you want to use to figure out what's the difference in electric potential. For electric potential energy, it's Q times V. Okay, so energy is equal to Q times electric potential, all right, if you have a charge of Q in the presence of the electric field. All right, so I think we kind of throw in the both electric potential and then the electric potential energy. Okay, so V stands for electric potential and then U stands for electric potential energy. So the SI unit for electric potential is volts. All right. Now just take a note that when we use the symbol, it's also V. Okay, so delta V. V stands for potential, but we also use volts as the unit. So V, the abbreviation are the same, but you should note like this delta V means change in potential, this V means volts, okay? Although their symbols are the same. All right, there's another unit you might be seeing. It's called electric volts. That's for the energy. It's the for one charge, electron charge, all right, that goes through a potential difference of 1 volts. Okay, so it's E, which is 1.6 times 10 to the negative 19 coulombs times 1 V. Okay, that gives you 1.60 times 10 to the negative 19 in joules. Okay. So if you have a positive charge Q in the presence of electric field E, if this is a positive, the charge, then it will go in the go in the direction of the electric field. Okay, so it goes in that way. So then the change in the potential will be equal to the negative of the work done divided by Q0. Okay, and then work equals to minus F times change in displacement or distance delta S over QZ, Q0. F is Q times E. So you can see then at the end, you'll have delta V equals to E times delta S, right? Because Q and Q cancel out. Now, if you just focus on the magnitude, then electric field, the magnitude of it should be equal to delta V over delta S, okay? Or a lot of cases, you'll see that people write the delta S as D, the distance, okay? So delta V could be equal to E times distance, all right? Delta S is the distance between the 2 points of interest. All right, so the positive charge oscillate in the direction of E field, okay? So that means over here, you would have actually higher potential, and then here you have lower potential because the electric force was doing positive work, okay? So then the potential will decrease. All right, we will take a look on the first example here. It says a uniform electric field of magnitude 3.8 times 10 to the 5th newtons over coulomb points in the positive x direction. Okay, so E field is in the positive x direction. Find the change in electric potential energy of a 7.5 microcoulomb charge as it moves from the origin to points A and B and then C. All right, so there's 3 parts here. So the 3 points are given in X, Y. So that means we are looking at 2-dimensional problem here from the origin here, X and Y. You have your E field to be in the positive direction. So that's your E field. There's this 6.0 and 0. There's this 0 and 6.0. There's this guy 6.0 and 6.0. 3 points. E field has a magnitude of 3.8 times 10 to the 5th. All right. And then this charge Q is equal to 7.5 times 10 to the minus 6 coulomb, okay, microcoulomb. Yeah, looking for change in electric potential energy. So you're looking for delta U. So in here, you can see if you are looking for delta U, you can find delta V first, then U delta U will be equal to Q times delta V, okay? So delta U will be equal to Q times delta V. And then for delta V, you can take this expression here, okay? Then forgot about Q here in front. Actually, no, Q is there already. All right. So if you are looking for delta U, then you would have Q in front, so minus Q from A to B, E field dot delta L. Okay. So E field is a constant, so you can actually put E field in front. So this would be minus Q E field dot integration of A to B times DL. Okay. Now for part A, it says from this point to over there. So then the path it takes is from 0 to over there. Okay. So then it would be this vector. This will be your change in displacement. So if you do this, this gives you just your change in displacement. That would be just 6 in y direction, right? Your E field is this guy in x direction, so minus q minus of 7.5 times 10 to the minus 6 coulomb times this 3.8 times 10 to the fifth. That's in I direction dot. So this integration will give you 6, right, in y direction, so j direction. And that should be in meters. Okay, I think they are given in meters. Right. 6 meters times that. All right. So I dot j will give you 1. Okay. I dot j, that gives you 1. So that cancels out. So you basically do the numbers multiplications. those three numbers. This will give you negative of 17.1 in joules. Okay, that's your delta U change in electric potential energy. Delta U. Okay. Let me know if you have questions on this. If not, then on B, it will be similarly. So this is minus Q of integration A to B, E field dot delta L. Again, E field is constant, so minus QE dot integration A to B DL. In this case, you are moving from 0 to 6.0. So then it's this guy. Actually, I'm sorry. I dot J gives you 0. So this one should be 0. Okay. I dot J is 0. It's not 1. So this, the first one will be 0 joules. I dot I will be 1. Okay. So in this case, you are moving from the origin to 6.0. So that would be 6.0 meters in I direction. Okay. So this will be minus 7.5 times 10 to the minus 6 coulombs, 3.8 times 10 to the fifth I dot 6.0 meters I. Okay. So I dot I will be 1. So this case will be minus 17.1 joules. Right. Part C is asking you if you go from 0 to there, okay, 0 to 6 over 6, 6 and 6. So again, minus QE, E is constant, dot A to B DL. In this time, you go from here to there, okay. So your displacement then is 6.0 I plus 6.0 J, right? That would be your disintegration if you go from A to B. It would be that guy. Then this is minus 7.5 times 10 to the 6 minus 6 coulombs times 3.8 times 10 to the fifth. That's in I direction, dot 6.0 meters in I direction plus 6.0 meters in J direction. Okay. You will only have this, the first term here count because I dot J will be 0. Okay. So then this will be the same result as you got in part B. Minus 17.1. Okay. Again, I dot I is equal to 1, but I dot J will be equal to 0. Okay. All right. Any questions you guys might have? All right. So if not, then we will take a look on energy conservation. So again, this is similar to when you have an object that moving under the influence of gravitational field. Okay, in this case, if you have an object that's of charge, okay, instead of an object, but a charge object, that is purely under the influence of electric field. So then the potential energy plus the kinetic energy should be equal to constant if you move from point A to B. Okay, that's the conservation of mechanical energy. All right, if this is a electric force. So if the charged particle is inside an electric field, then electric potential energy is Q times V. All right, so you can replace UA as Q times VA and UB as Q times VB. All right, so then if you rearrange the terms, if you move UB to the other side of the equation, so then 1/2 MVA squared plus UA minus UB will be equal to 1/2 MVB squared. If you are looking for VB, okay, then you can solve for VB in that way. That's from that equation. Okay. Now UA minus UB will be equal to Q of VA minus VB. All right. Potential energy is equal to Q times potential. Okay. All right. So we'll take a look on one example here. This one says a proton has an initial speed of 5.5 times 10 to the 5th meters per second. Okay. There's some information that is hidden here. So a proton, it has a fixed mass, right? It's one of the fundamental number for the mass of proton. So that means you would have the mass of the proton. So 1.64 times 10 to the minus 27 kilogram. And then you would have the Q for a proton, that would be 1.6 times 10 to the minus 19 coulombs positive, okay? And it tells you it has initial velocity of speed of, so you can say VI initial or VA if you want, but 5.5 times 10 to the 10 to the 5th meters per second, okay? So you have three numbers already given. It's asking you what potential difference is required to bring the proton to rest. So this is your initial speed, and then final speed, it should be 0 because now the proton comes to a rest, okay? So it's asking you what would be the delta V. So let's just go back one slide here and then talk about the symbols here. Okay, so you can see in the equation over here that you are using over here, there's small vb, lower vb, okay, and then lower va. There's capital Va, capital Vb, okay. So capital V's, they stand for the potential, electric potential, okay. Small v's, they stands for speed, okay, the speed of the object, okay. All right, so in this case, you're looking for delta V of capital V, which means potential final minus potential initial. Okay. So what will be this potential difference? You can use the equation of 1/2 mv. All right. Now, if you do vi, small v, okay, so let's do small v square. That should be equal to 1/2 mv initial or mv final square plus q times, right? So I think it says v. All right, so if I have v final here, okay, then I should put the v final in front minus v initial, okay. Then I is b, then this is b, okay. This is a, this is a. All right, basically I'm looking for this delta v. I think we can take a look here together, okay. So we're looking for this. You move this guy to the other side of the equation. So then 1/2 mv initial minus 1/2 mv final square, right? Equals to Q times delta of capital V. And then you can divide both sides by Q. So you have your delta V, okay? It tells you the initial speed, the final is 0, Q, you have it 1.6 times 10 to the negative 19. So this will be 1/2 of 1.674 times 10 to the negative 27 kilograms times 5.5 times 10 to the 5th square, okay, minus should be 0, right? Because V final is 0. Divided by 1.6 times 10 to the negative 19 coulomb. Okay, that will give you the potential difference. It gives me about 1.54 times 10 to the 3rd volts. Okay. So that's A. And then B is asking us what potential difference is required to reduce the initial speed of the proton by a factor of 2. So this time, V final, small v final is not 0, but it's 1/2 of 5.5 times 10 to the 5th, or 1/2 of V initial. Okay. So we'll be using the same equation here for delta V potential difference, but change the V final speed to be 1/2 of initial one. Okay, so then in this case, then your delta V, capital V, is equal to 1/2 of initial V squared minus 1/2 of M times 1/2 of initial V squared, right? Divided by the Q, the same Q. All right. So if you square the 1/2 here, it gives you 1/4, right? So this is then 1/2 MVI squared minus 1/4 of 1/2 MVI squared. This 1/4 is just coming from square of 1/2, okay? That over Q. So this is 1/2 MVI squared. This is 1/4 of 1/2 MVI squared. So then on the top, you'll get 3/4, right, of 1/2 MVI initial square, and then divided by Q. That will be your delta V, right? So I'm doing this trick bits because I know that the initial, this term, 1/2 MVI squared over Q is equal to this guy, right? That's what we calculate already. So then this is equal to 3/4 times 1.54 times 10 to the 3rd volts, okay? Of course, you can plug in the numbers, okay? But that's this trick we can play so we don't have to plug in all the numbers one more time. This gives you roughly about 1.2 times 10 to the 3rd volts here for this new potential difference. Okay. For the last part, C here is asking you what potential difference is required to reduce the initial kinetic energy of the proton by a factor of 2. Okay, so that means your K final, your final kinetic energy, or your final kinetic energy is 1/2, right? Kf, that is 1/2 mv final square. That's equal to 1/2 of the initial Ki, kinetic energy. So 1/2 of 1/2 mvi square. Okay, so that basically tells you that you'll be using the same equation to calculate your delta V, this guy again. So your delta V will be equal to 1/2 mvi square minus 1/2 mv final square divided by q. Okay, now this time, this term is equal to 1/2 of this. So this guy. Okay, so then this is 1/2 mv initial square minus 1/2 of 1/2 mv initial square, right, divided by q. So then this is initial kinetic energy. This is 1/2 of it. So then it's 1/2 of the initial kinetic energy square, right, divided by q. That'll be your delta V. Again, this guy, the initial 1/2 mvi square divided by q is 1.54. So you can just take that number down in the place of this expression. So 1/2 of 1.54 times 10 to the third. That would be 7.7 times 10 to the second volts. Okay, for your potential difference required. All right. All right. Okay. So now we are going to take a look on electric potentials, various case by case, like various scenarios, case by case. So first, let's take a look at the electric potential by point charge or systems of point charges. Okay, so if you have point charge, now we know that delta V change in potential energy. So if you have a point of interest, and then if you have your reference point, okay, so if there's a point charge over here, now your point of interest over here, and then this is your reference point. So then what will be the potential difference between these 2 points? Okay, so you do potential of this one minus that one, that gives you delta V. Now we know delta V, you can do minus integration from your point A to your point B, okay? So B is your point of interest, A is your reference point, times E dot delta L, okay? And for electric field produced by the point charge, we know it's KQ over R square, right? So then E field is equal to KQ over R square, okay? So times dr, okay, will be the change in the displacement there. Okay, so you can see that actually I think you can do right. So this is E field over here. Okay, and then dr. So you can see if you are at this point over here, then this is the direction of your electric field. Okay, so then for dl here, you'll just take the component that is in this direction, and then the component that is perpendicular to this direction will give you 0, right? Because E dot dl, if they are perpendicular to each other, then it will give you 0. 2 vectors perpendicular to each other, dot product will be 0. Okay. All right. So typically you take the reference point to be when this it's far away from your point source, so that the reference point will be having zero potential. Okay, so usually you take infinity far away to be your potential reference, and then the potential of zero. Okay, so in that case, if you integrate through that, then this guy will give you uh, minus kq integration from reference, which means infinitely far away to point P, okay, 1 over r squared and then dr. That gives you 1 over r, positive 1 over r, okay? And then take this as infinity, then v will be 0, okay? So then for v equals to, in this case, it will be just equal to kq over r, okay? So then this is the potential, electric potential for a point charge, okay? So if you have a point charge, it's that. Now just keep in mind the potential is a scalar, okay? So you don't have to worry about the directions of it. So it's kq over r. And then for electric potential energy, simply you multiply by the charge Q, okay, or Q naught in this case is the test charge. So then U will be equal to K Q naught Q over R. So Q is the source charge, Q naught is your test charge, okay? If you have a test charge close to the source, then that would be the potential. The potential is 0, okay? Now, if you have a system of point charges, then you do summation of the potentials, electric potentials by each of that point, those point charges. Okay, so if you have a system of point charges at point P, you simply just doing summation of KQI over RI. Okay, um, so this is a scalar summation. Okay, so just add them up algebraically. Okay. So we'll take a look on one example here before we move on. This one says, in this figure, there's Q1 and Q2. Q1 is positive 1.8 nanocoulombs, and then Q2 is minus 2.1 nanocoulombs. The side length of the square is 0.10 meters. What's the electric potential at those 2 points, A and B? So you have 2 point charges. Okay, you have you are calculating for the electric potential at 2 locations. All right, so let's take a look here together. So you have 2-point charges. Then you need to add the potentials by those two charges together, okay, for each of the point of your interest. So then you'll be doing K Q1 over R1 plus K Q2 over R2, okay? In the first scenario, this is your R1, so R1.10 meters. This will be your R2, right? From here to A, this will be your R2. So because this is a square here, so the diagonal of a square will be equal to, this is R2, square root 2 of A, right? 0.10 meters. Okay, so square root of 0.10 meters for that guy. K is the same, 8.99 times 10 to the 9. You can put the A in front, the K in front. All right, and then Q1 is 1.8 times 10 to the minus 9 over R1.10 meters plus Q2 is minus 2.1 times 10 to the negative 9. Okay, so on that, R2 will be square root 2 of multiplied by 0.1 meters. Okay, so that will give you your VA. It's about 28 volts. For the second part, you'll be doing the same, but this time R1 and R2 changes, right? So this time, this will be your R1. It's the distance from Q1, so this will be square root 2 of 0.1 meters, okay? And then this will be your R2. So basically, you're switching R1 and R2. So K of Q1 over R1 plus K of Q2 over R2, the same formula, 8.99 times 10 to the 9th. Now this time you put 1.8 again, but at the bottom here you put square root 2 times 0.1 meters, okay, plus negative of 2.1 times 10 to the minus 9 over 0.1, right? That will give you about negative of 74 volts. Okay. You can see that if you are surrounding a positive charge, electric potential is positive. Okay. If you are surrounded by a negative charge, then electric potential is negative. So this is a negative charge. Q2 is a negative 1. Q1 is positive. Okay. Any questions you guys might have? All right. So let's take a look on the electrostatic potential energies. Okay. So that's assuming if you have already a Q1 in space. Now, if you bring a second charge Q2 in space, all right. So then you need to do work against the electric field in order to bring the second charge in, right? So the work needed to be done is equal to Q2 times V2, all right? So if now you have Q2 is at distance of R12 away from the first one, okay? So that's the separation of the two charges now in space. Then V2 is KQ1 over R12, right? Just KQ over R. All right. So then the work done will be Q2 times the V. All right. Now imagine if you are bringing a third charge close to Q1 and Q2 that's already in space separated by R1 and 2, then the work needed will be equal to Q3 times V3. Okay. If 3 is at a different location, then the work done will be this guy, Q3 of V1, all right, plus Q3 by the second charge. Okay. So this guy here. So then you can see by putting those three together close to each other in space, the total work will be the work done by bringing a second one plus the work done by bringing a third one. Okay. So you need that much of work, okay, to put the three charges close in space. Then you add those three terms up, this guy plus this guy plus this guy. Okay, so you can see this is K Q1 Q2 over R12, K Q1 Q3 over R13, and then K Q2 Q3 over R23. Okay, so that's the amount of work needed. So that means that's the amount of the energy, electric potential energy being built, okay, on the system. Now, also think about for the system of three charges in space close to each other. So Q1 times V1, all right, so that's the electric potential energy on Q1. That is equal to, you'll have potential by the other two charges, okay? So KQ2 over R12, KQ3 over R13. So then you have those two terms, KQ1, Q2 over R12 plus KQ1, Q3 over R13. Similarly, for the second charge, you can write the same similar expression. You get these two terms add up together. For the third charge, you will get those two terms, okay? So then U is equal to, as we derived in the previous slide, equal to those three terms, which means 1/2 of these three add up, okay? Q1 V1 plus Q2 V2 plus Q3 V2, because each of these terms have two terms, okay? And then they are repeating, like this one is the same as this one. This guy is the same as this guy. This guy is the same as this guy, okay? So then in general, the electric potential energy for a system of I charges or n charges should be equal to 1/2 of summation of from I equal to 1 to m QIVI. Okay. Q is the charge of the I, and then V is the electric potential at that charge Q. Let's take a look this one where it says 3-point charges are on the x-axis, Q1 at the origin, Q2 at x equal to 3, and then Q3 is at x equal to 6. Find the electrostatic potential energy of the system for if Q1 and Q2 are the same, 2.0, and then Q3 is minus 2.0. They are in microcoulombs. So this will be R12, this will be R23, And then from here to here will be R13. Okay. R12 is 3 meters. R23 will be also 3 meters. R123 will be 6 meters. Okay. And we also know their Q's, their charges. Okay. Q1 and Q2 are the same. 2.00 times 10 to the minus 6. Q3 is negative 2.00 times 10 to the minus 6. Okay. So in general, U is equal to 1/2 of summation of I QI VI. Or U is equal to K Q1 Q2 over R12 plus Q1 Q3 of R13 plus Q2 Q3 of R23. If you go over here, you can see you can use either this one or you can use that one. Right. So it looks like we have Q1, Q2, Q3, and then R12, R13, R23. So we can just use this part over here. Okay. All right. So I think you simply plug in the numbers. So Q1, Q2, Q3 are having the same magnitude, but Q3 is negative. Okay. So Q1, Q2 then will be just 2.00 times 10 to the minus 6 square. Q1, Q3, it will be the square, but with the minus sign because Q3 is negative. Okay, and then also on this one, it should be negative of that 2.00 times 10 to the negative 6 squared. Okay, over 3, and then the second one will be over 6. The first one will be over 3. Okay, just pay a little attention to the distance there as well. All right, and then that will give you minus 6 times 10 to the minus 3 joules. Okay, that's the energy of the system. So that means actually, yeah, for this kind of system, okay, so they you don't actually require extra work, okay, to put them together. All right, I think we'll stop here today. Okay, we'll come back tomorrow on the rest.